Hello and welcome to our webinar today. Today we have a very exciting topic for you. We are going to discuss commercial PV system design with Fronius inverters. And joining me is my colleague, Cyprian Okolo. He's the technical sales advisor for Western African region based in Lagos, Nigeria. And myself, David Mwangi, I'm the technical sales advisor for the Eastern African region. I'm based in Nairobi, Kenya. In our agenda today, we are going to discuss a few topics. So we will start with going through which Fronius devices are available for commercial systems. Then we look at plant design considerations. Then we look at design tools that can be used for commercial systems design, system layout, at which point Cyprian is going to take over, and cabling and power loss calculations, installation hints, as well as data communication and plant control. Then at the very end, we will give you further information. As usual, before we start, feel free to ask any questions you have during the course of this webinar. Please put them in the questions area, and we will do our best to answer these questions as we go along. In addition to that, if you have a specific feedback about this webinar or any webinar topics that you'd like to be covered in future, please also feel free to let us know, and we always appreciate your feedback. So let's get into it and start with the Fronius devices that are available for commercial systems. So in the Fronius Solar Energy portfolio, we have a specific hardware that are categorized depending on the power class. And on the inverter side, we have, for example, what we can call residential or home application inverters, and then we have the commercial. In the residential, for example, we have Gen 24, Gen 24 Plus hybrid inverters. And of course, we also have the Fronius Snap inverter up to about 12.5 kilowatt. In the commercial segment, we have the Fronius Tauro, we have the Fronius Simo Advanced, and we also now have a new entrant into this category that we are calling the Fronius Vato. When it comes to sector integration and components that are necessary, which could be used mostly for either, let's say, commercial or residential systems. If you look at the Ohmpilot, for example, for EV charging, we have the Fronius Ohmpilot for excess energy management that allows you to generate hot water with your PV system. And we do have also the smart meters that allow you to see or to visualize the energy flow within your setup. So going into details about these components, very briefly about them, we have the Fronius Echo available in the power class 50 and 100 kilowatt. This inverter has 1 MPPT with an operating MPP voltage of 580 to 930 volts. The weight, respectively, for the 50 and 100 kilowatt would be 74 and 103 kilograms. Looking at the Fronius Vato, which is a new small to medium commercial inverter range, we have the power classes available from 25, 27, 29.9, and then 33.3. So if you look here, it sort of overlaps an existing Snap inverter, which we refer to as the Fronius Snap Inverter Echo. And therefore, naturally going forward, this Vato inverter is going to replace the Fronius Snap Inverter Echo. One key differentiator here would be the possibility for asymmetric feeding, but currently this is designed for single inverter systems. Getting deeper into the Vato, to give you specific info about this inverter, we have a huge departure also in terms of the available MPPTs within the inverter. This inverter has now 4 MPPTs. I think we are used to the Snap inverters, especially the Simo and the Primos, that have 2 MPPTs. but this inverter now incorporates 4 MPPTs. And for each MPPT, you can connect 2 strings with maximum usable current per string of 28 amps, as well as maximum current for each MPPT will be at 28 amps. Open circuit voltage will be 1000 volts, and MPP usable voltage range is in the range of 150 to 870 volts. Usable DC power per MPPT is about 13 kilowatt, and yeah, maximum PV generator output at 20 kilowatt per MPPT. As usual, it also incorporates the dynamic peak manager, which is quite common for all Fronius inverters for shade mitigation. Another huge departure would be the integration of both AC and DC SPDs within the inverter. We are used to only DC SPDs for snap inverters, but the inverter now integrates right from the factory both AC and DC SPDs. So this can be a choice between, on the AC side, either type 1+2 or type 2. And respectively, also for the DC side, you can choose between type 1+2 or type 2. So, but I think in our market, we are going to have an inverter retrofitted with only type 1+2 on the DC and AC side. So this offers maximum protection against over voltages on both sides. Then we do also have an existing inverter class or series, which is the SIMO Advanced. So it's very similar to the existing SIMO inverters. The only thing that has been added is the AFCI, which is the arc fault circuit interrupter. If you look at the power classes, these are exactly the same as the existing SIMO series. So we are starting from 10.3, 12.5, which are pretty much like residential class inverters. But then starting from 15.0 up to 20.0, this would be inverters that are quite nice for small to medium commercial systems. Just remembering that you can use multiple inverters, like the 15, the 17, 20, you can mix all them together to do a commercial system. So all the other specific details remain the same. So we have still 2 MPPTs within this inverter, and here we can see the current carrying capacity for each of the MPPTs per power class. Oversizing still remains at 150%. Another important component for commercial systems would be the commercial smart meters. And in this class, we do have the existing 5 kiloamp 3-phase smart meter. That is an ideal product when you're doing commercial systems where cables diameter in cross-section are bigger than 16 millimeter square, and therefore a CT with the secondary current of 5 amps is required. But we've also introduced a new smart meter, which we are referring to as the IP, the smart meter IP. This is also a 5 kiloamp smart meter in 3-phase. And this is ideal for use where you have long distances from the feeding point to the inverter. So, because as we know, the normal Modbus RTU connection for Fronius is recommended at not more than 300 meters. But with the Fronius smart meter IP, if you have long distances or a very complex compound where there is no straight line where you can do your cable layout, then the smart meter IP becomes very helpful. So this requires also some CTs with a secondary voltage of 333 millivolts. So the motivation here for the smart meter IP in the commercial segment is to overcome large distances as well as obstacles like I've mentioned. So with this product, then commercial customers can use, for example, existing Ethernet infrastructure to bridge the long distances where we have obstacles between the inverter and the feeding point. So we have here the various channels of communication, data communication for the smart meter IP. We have the communication via Modbus TCP. We have Modbus RTU, as usual. We also have a Wi-Fi connection. So here you can do both Ethernet and Wi-Fi. So you do not necessarily have to connect an Ethernet cable to this smart meter. You can connect, if you have a strong Wi-Fi signal, you can go through the Wi-Fi channel as well, which is also Modbus TCP. And also another departure is the use of waggle clamps. So in this case, you do not need to screw the cables to the smart meter. You can use very easy to integrate or to secure waggle clamps, and that also realizes very fast connection. So in terms of compatibility, the smart meter IP is compatible with all the commercial Fronius smart meters, the Tauro, the Vato, as well as the SIMO Advanced, including also sector coupling components such as the Ohmpilot as well as the Wattpilot. Now getting into the plant design consideration, once you have understood which Fronius components can be used for commercial systems, what you consider when you're designing a commercial system would be eventually the total cost of ownership. And the total cost of ownership then comes from the CapEx consideration, which is the capital expenditure, plus what are the anticipated operating expenses. So once you put these two together, then you arrive at what will be the total cost of ownership of this particular system. So breaking it down, when you talk about CapEx, then you have quite a number of things that you look out for. You have to consider the impact on of the PV modules on the cost, overall cost, the balance of system costs, labor costs, and so forth. But if you look at, for example, the cost of the inverter within this setup, so you can see in this pie chart, the inverter would only take about 9% out of the entire CapEx or the capital expenditure. But the inverter can have huge benefits or huge saving potential when, for example, you're looking at the balance of system component. So in terms of this, then you can have the possibility to influence this cost, which is about 21%, by choosing the right inverter for your commercial setup. So this is where the inverter gives you the greatest saving potential. So when planning for commercial systems and how you then choose your inverter, there are two methodologies. The classic methodology would be to look at the cost of the inverter as your first consideration. What is the cost per kilowatt of this inverter or per watt? And then in terms of the power class, which inverter power class do you want to use? Which design topology are you going to use? Is it a centralized layout? Is it a decentralized layout? Then you think about the selection of additional cost-effective components. And this is where you are talking about the balance of system, for example, and then the distance from the PV generator to the transformer. So this is the classic consideration when you go in the order of 1, 2, 3, 4, then 5. But when you are, for example, considering to use the Fronius Tauro, you actually go in the opposite direction, because the Fronius Tauro would offer you quite a bit of flexibility. And therefore you can start considering, for example, what is the distance of my PV array to the feeding point, which kind of balance of system components do I need, the design topology. Then at the very last thing you think about when you are talking about the Fronius Tauro inverter would be the cost per watt, because the Tauro does help you to offset quite a number of other associated costs, or to minimize on the associated cost of a commercial setup. So with the Tauro, for example, you can realize a central or decentralized design, and just going to differentiate the two. With the central design, then you have all inverters placed at one point, which allows for easy transportation and access to all the inverters. If you're going to do service, for example, then in this case, you do need to pre-combine all the strings in a DC combiner box, and then you transport the DC power to the inverter using bigger cross-section DC cabling. On the flip side, you have the decentralized design that requires that all the inverters are distributed across the PV plant, The module strings are then directly connected to the inverter. For example, for the Tauro, then you would use the already integrated MC4 plugs. And in this case, no additional DC combiners would be necessary. In terms of the design tools that can be used for this work, we, for example, have our free solar creator. So this is a free tool that can be used by anybody without any limitations. The only thing you need is to register for an account. So you then calculate all possible designs. So this is for basic designing. If you do require additional modeling, then this can be done with professional tools. And these professional tools, for example, are PVSol, PVSys, and so on. And the reason why Fronius does mention quite a bit PVSol and PVSys is because the data there is always to date as far as Fronius inverters are concerned. However, if you have to use only an external design tool for commercial systems, it is possible that you're going to overlook some possible recommendations as far as inverter choice is concerned. And the reason for this is that different programs will use different inverter data for calculation. And therefore, we always recommend, even when you're using these other professional third-party design tools, to always go to the Fronius Solar Creator to double check that what you have chosen for your PV system is the best configuration possible. In addition to the already mentioned PV system, PVSol, you can also use, for example, PV Scout, PV Plan for Solar, and also Polysun as additional design tools. So when it comes to the configuration using the Fronius Solar Creator, here you can flexibly design a comprehensive solution. Then you simulate how the PV system is going to interact with your inverter, with your electrical load battery system, as well as an EV charging network if one is to be designed. Just to show you what is possible, in the string configuration check, where you can do a PV check within the Solar Creator, you can take if a certain module very quickly that you want to use with the, any Fronius inverter is going to be compatible depending on how the IV characteristics of this module is. So, for example, here we have simulated something with a Jinko 400 watt module. So our inverter of choice is a Cymo 20, and the other details are shown. So what we have arrived at is a list of possible configurations for this simulation. And per the Solar Creator, we have a potential use at an inverter ratio, meaning the DC to AC power ratio of about 120%. So therefore, for this Cymo 20, we are going to connect up to 24 kilowatt peak on the DC side, meaning we can have connections to the first and the second MPPT. The first MPPT would take 2 strings of 17 modules each, and the second MPPT will take 2 strings of 13 modules each. So therefore, when it comes to the connection, it's just now a question of matching those strings accordingly. So we said the first MPPT is going to take 2 strings of 17 modules each, and the second MPPT is taking 2 strings of 13 modules each. Just remember that for the Cymo 20, you have the possibility to connect 3 strings for the first MPPT and 3 strings additionally for the second MPPT. But connecting 2 strings only for the first MPPT and the second MPPT also taking 2 strings is not a problem at all. When it comes to the Tauro side, for example, if you are designing a bigger commercial system, then you could have up to 4 strings on, although we said that the Tauro Echo has 1 MPPT, it is divided into different DC connection areas. So for example, you could have PV1, which is DC connection 1 for the Tauro, taking 4 strings of 17 modules each. And then you could also have the second string connection or configuration for P2 or DC connection area 2 with 4 strings of 17 modules each. So there's quite a bit of flexibility depending on if you're using, for example, the direct version of the Tauro, which already has integrated MC4 plugs, or if you want to, like we said, with a centralized design topology to pre-combine your strings, then you also have the flexibility with the Tauro inverters to order a pre-combined Tauro configuration that allows you to connect up to 4 DC cables into the inverter. And at this point, I would like to hand over to Cyprian, who will take over and do the remaining bit of it. So, Cyprian.
Yeah, thanks a lot, David, for the wonderful presentation. Yeah, so I will be continuing from this point. So I want to believe that my screen can be seen and because my audio is clear. Great, so without further ado, let's continue. So shall we be continuing with system layout? Okay, so let's begin with the general PV array design. So this can actually be calculated for modules, of course, in series with this particular equation. So in order to calculate the number of PV modules, maximum number of PV modules for per design, it can be given by this particular equation, VD max minus VOC all over BMPP. So they are all defined here, where VD max for the inverter is basically the maximum inverter input voltage, otherwise known as the maximum DC voltage that the inverter can handle. VOC for module, it's basically the module open circuit voltage, also known as the voltage output of a single solar panel when it is not connected to any load or to the inverter. And then VMPP max is basically the panel or module's maximum power point voltage, otherwise known as the voltage at which the solar panel produces its maximum power, which is sometimes basically about 80% of the open circuit voltage. So, but please note here that it is important to note that this equation only determines the maximum number of panels that can be connected in series. So other factors such as shading temperature and other factors like panel orientation should also be considered when designing. So this is basically like an equation that you could use to test run what would be obtainable when designing or trying to calculate for the number of panels that can be used or implemented for a system. So let's now talk about the solar panel orientation. The general rule is that PV systems in the Northern Hemisphere should have the panels facing the true south or geographic south. Conversely, the PV systems in the Southern Hemisphere face the true geographic north. And for the Southern Hemisphere, if more energy, for example, is used in the mornings, then well, most of the panels or modules should face northeast. And then if reverse is the case, if more energy is used in the afternoons, then the panels should, most of the panels should face northwest, because basically the sun rises from the east and sets in the west. So depending on the power usage per period of the day, that will determine the density of modules that would be oriented either east or west. So going forward, the angle that the solar panel should be set at to produce the most energy is given in a given year is determined by the geographical latitude. Although this is generally the case, but then there are still some other factors that are keyed in that's not actually covered in this webinar. But then eventually the exact figure is usually not too far from the geographical latitude. So it now holds that a general rule for optimal annual energy production is to set the solar panel tilt angle equal to the geographical latitude. Okay, so basically what we mean by that is, for example, Cape Town, that has its coordinates. Cape Town, of course, is in South Africa. That is located at latitude 33.9 in the southern hemisphere, of course. So it means that the latitude is therefore minus 33 degrees because it is below the equator, and then hence the tilt angle for such panels would be 33 degrees facing north. So that once the sun is moving or rotating, sorry, once the Earth is rotating, of course, around the sun, it of course does this around the equator, and then when it does this, and for regions in the southern hemisphere, you would have the panels tilt facing north to get the best irradiation. So, so basically speaking, it is the tilt angle that we've been discussing about. What it basically means is that the best way that the panels can actually get the best irradiation from the sun is to ensure that the sun rays incidence on the panels at a perpendicular angle, basically speaking. So that's what we're talking about. So, and yeah, so as you can see in this case, it is assumed that these panels are actually tilted corresponding, that the tilt angle is corresponds to the respective latitude of this particular area. So going forward, we'll have a look at east-west orientation on commercial system, because this actually pops up in cases where we have systems comprising of single MPPT inverters. Of course, it is the quest to achieve the highest level of self-sufficiency. This, of course, can be helped by, of course, the efficient use of space, of course, by generating higher PV power. It is expected that for shaded systems that also has steep angle of inclination, for such systems to have it split into smaller devices, so that these split systems will take care of the respective steep inclination angles. So what we're saying in effect is that for the design for east-west orientations, it is expected that when dealing with single MPPT string inverters, to ensure that mismatching losses are brought to the barest minimum. Well, an advantage that such system comes with is that it is cost effective. Over dimensioning is possible, but then a solution for such complex rules has been provided by Fronius with the introduction of the Varto. By the way, the Varto inverter will be introduced to the market in a couple of weeks' time. So, having said so, it is of course important to take note of these design rules. The number and type of modules implemented for such systems must be identical in all strings. Please ensure that as much as possible there is no shading, and then also ensure that all the modules within the same string has the same angle of inclination. So, putting a bit of context to it, we're going to have a look at the centralized system. So what we're saying is basically for east-west orientation, it is possible to have all the modules facing due east connected to a particular inverter. Although, of course, this is a centralized system, so it means that the power is collected from the modules using DC combiner boxes, and then this is now channeled to a centrally located inverter system. So this is basically for all modules facing east. Same thing would also be done for all modules facing west. And then these can be collected to centrally located inverters, which is of course where it gets the name centralized inverter or topology. So same thing can also apply for a decentralized topology. So in this case, for decentralized, you have the inverters installed or implemented pretty much close to the modules because they're connected directly to the inverter. So once the DC or the modules are connected to the inverter, you can now have a long run of AC cables. So we have all the modules facing east and west connected to their respective inverters and then to the main distribution frame. So the assertion is there that single MPPT inverters are disadvantageous to or cannot match the requisite power density as multi-MPPT inverters. But then with the Fronius Echo, because the Taro Echo also, it has actually been proved that from research that has been done that it is actually possible to obtain optimal power so long as these conditions are applied. Of course, I've mentioned these conditions in a couple of previous slides. So this was actually brought into context with this particular investigation or research that was done with modules or particular systems connected roof. Some were connected oriented roof with east-facing orientation to one panel, as you can see. And then other panels or modules facing west were connected to another single MPPT inverter. Details are all here. The inclination angle, as you can see, 10 degrees, 18 strings, and then 18 modules, and then we have 12 strings of modules connected in this manner. So for the east-oriented modules, generation was 118.8 kilowatts, same as the west-oriented panels. And then in order to test out this assertion or to prove the assertion wrong, so we had the same number of modules connected on a roof, but this time around we had 12 modules connected to one inverter and then another 12 modules connected to the other inverter. But this time around we had 6 facing east and 6 facing west connected to the respective inputs of the inverter, as you can see. And this generated exactly double of what the other oriented east and west inverters were producing, as you can see. So the results are here. So for the east-west orientation, we have east and west orientation, we have the respective yields per year. And then by the time you now make or take the difference between the yields for the east plus the west system, that is the first and the second, and then compare it with the east, the modules connected to the east-west orientation, it is seen that there is a positive difference of up to 45.77 kilowatt hour, which of course proves that so long as the predefined conditions are met, being that all the modules must be inclined at the same angle and ensuring that all the modules are of the same specification, then you can be sure that there will be virtually no mismatching losses. So still continuing with the commercial topology with the Taro. So we're going to have a look at a 1 megawatt PV installation on a free field. So it is possible to have it this way. So we'd have, since the inverters are the modules are connected directly to the inverters, you would, for this particular case, have the respective AC runs coming from each of the inverters. So we have 8 inverters here, so we're expected to have 8 long runs of AC cabling. So the advantage of this particular topology is that you don't need any additional DC combiner boxes, and of course planning is basically easy. So you can have it in this way, or you could have it coming with the advantage that Fronius brings to us, which is the Tauro AC daisy chaining option. So if you notice from the previous topology, you can see that we had 8 long runs of AC cabling, but in this case, we're just having 4. And this is made possible because we're able to AC daisy chain 2 inverters. So instead of having 2 long runs from these 2 inverters, we're just having 1 run of AC cabling to the main distribution frame. Of course, the advantage comes as the previous occasion, no additional DC combiner boxes. But then most importantly, you have shorter AC cable runs, which of course implies to a lower cable cost. And this is of course a very, very important component in terms of achieving lower BOS cost. And then of course it also translates to less installation efforts when it comes to the cable laying. So talking about cable and power loss calculations, let's quickly look into that by finding out how the power losses across these cables can be calculated. Well, basically we have a basic formula for it. The formula for power loss is simply P, which is the power loss, is equal to the resistance multiplied by the square of the current. So basically P is equal to R times I squared. But then note that R, which is the resistance, is also equals to the specific resistance times the length of the conductor all over the cross-sectional area of the conductor. Rho here, or specific gravity, basically specific resistance basically stands or represents the resistance of that particular material or the material in question to the flow of current through it. So by the time we replace R with this particular definition of R, which is rho times L over A, so that brings power loss across the conductor to be rho times L over A times I squared, or simply put, just basically putting it all together to make it a bit simpler. So that's how you calculate your power losses, where P is equals to power, R is electrical resistance as earlier defined, I is electrical current, rho is the specific resistance, L is the cable length, and of course A is the cross-sectional area of the conductor. So having gone through this defining process for power losses, we're going to make some basic deductions. So these deductions are that it is now obvious that power losses are inversely proportional, or the power loss is inversely proportional to the cable's cross-sectional area. What does this mean? It means that the larger the cable cross-section, the lower the losses. Okay. Now, in addition to this, if you double the current, it's going to yield 4 times the power losses. So this is also obvious. And just to give us an example, let's say that these figures or these variables all have unit value meaning 1. So if the power loss is defined, if with specific resistance, cross-sectional area, length, and current are all equal to 1, we're basically going to have a value of 1, because 1 times 1 times 1 squared over 1 gives us 1. Now, if we decide to double the current, so say I, which is correct, is equal to 2. So 2 times 2, or 2 squared, gives us 4. And then 4 divided by 1 is 4. So that, of course, proves what this deduction that we have made here. So that now behoves on the system design engineer to take note of these respective deductions, as it would help to design the most economical PV system. So yeah, so you would now want to ask, what cable lengths are then possible to run for a particular cross-sectional area? Well, you might want to ask it because it is also some of like a demand that power losses shouldn't be greater than 1%. Okay, so you might now want to ask, okay, what is the maximum cable length, AC cable length, that can be achieved with, say, for example, 240 squared AC cable and a tower 100 kilowatts without having losses higher than 1%. So this has actually been looked into, and it has been arrived that taking into account that the cable losses should be less than 1%, the maximum AC cable distance of 125 meters is possible, which is actually a good figure. But then, having said so, let's also note that there are systems that are actually designed for power loss of greater than 1%, but less than 3%. However, there are no normative requirements that prohibits the power loss going greater than that. But then, this has an effect on the monetary loss, which is why it is imperative that the power losses are kept to the barest. So this will be seen in the next slide. So how high are the monetary losses when it comes to the implementation of cables with their respective cross-sectional area? Well, so an example has been made here for the monetary losses for a 2 megawatt peak system, and with an extrapolation of over 20 years on the AC cabling, and then with an average length of 125 meters. So as you can see, we have figures already. So for a 240 squared over 20 years with this particular length, we're going to arrive at an equivalent monetary loss in terms of the equivalent power losses to the tune of 16,173.44 euros. We can see the respective costs for other cross-sectional areas. Then the list here is 95 squared with a cost of 40,858.65 euros. So if you now take the difference between the highest here, which is 240 squared, and 95 squared, we will be arriving at a whopping difference of 24,685 euros difference over 20 years. So we can see here clearly that the cross-sectional area of cables being implemented is definitely very, very important. So this is something to take note of while designing your PV system. So what's the best system topology to implement? Yeah, so taking into consideration of Taro system that includes all these losses over 20 years, and then of course considering the distance from the PV system to the main distribution frame, which has been plotted with the cost 200 kilowatts PV block, it can be seen that in the initial stages, the pre-combined capex cost, it's relatively high than the direct, but then over time, the OPEX cost makes it economically viable. And then we can also see that for the direct, it comes with lower costs compared to the pre-combined. But then as time goes on, and due to OPEX cost, it makes it not too economically viable when compared to the pre-combined. But then we can see that this is a function of the distance from the PV system to the main distribution frame. So we can see that, of course, there's a break-even point here, which is around the 50-meter mark. So this behoves to explain this, meaning that for shorter distances or for distances ranging from 0 to 50 meters, it is best to go with the Tauro direct topology. And then the system design exceeding 50 meters distance from the PV system to the main distribution frame, it is best to go with Tauro pre-combined topology. So basically speaking, if you're going for shorter distance, go with the direct topology, then pre-combined for longer distances. Good. How about data communication and plant control? So for data communication, system data can be transferred in parallel to third-party components and, of course, to Fronius accessories like the Fronius Solar Web, of course, where Modbus TCP, Modbus RTU, and of course, where the Fronius Solar API using the JSON protocol, as you can see. In terms of plant control, thanks to the introduction of the system power control, it is now possible to achieve feeding limitation using this particular algorithm. And to make things interesting, there is no need for any additional software or hardware, any additional hardware, sorry. All that is needed is basically a software upgrade or update. Once that is done, then your system will be able to achieve feeding limitation. But then points to note here is that for a system with a backup setup, that is with a Fronius Gen 24 Plus, that Fronius Gen 24 Plus will automatically be the master in the system. So let's break it down. It is possible to achieve dynamic feeding limitation for up to 20 inverters, and you can have solutions for mixed inverter systems. So you can have this particular solutions implemented for systems containing Tauros, snap inverters, Gen 24 and Gen 24 Plus inverters. It is, of course, also possible to have a SolarNet ring within this setup, but then it is advised that to have a maximum of 5 inverters per SolarNet ring, meaning 1 submaster and then 4 slaves, basically speaking. Major components of communication here, of course, will be just 1 smart meter, and then communication channel is via Modbus TCP. So like earlier said, this will come with the latest software update, version 1.31, which will be coming up or being rolled out in a couple of weeks' time. So to bring it into context, for snap inverters and Gen 24s generally, like I mentioned earlier, if you have a backup system, then ensure that the Gen 24 Plus inverter in this particular backup system is the master. And then connecting, if it's one comprising snap inverters and Gen 24, of course, you'd have a setup, like as mentioned earlier, but ensure that every SolarNet ring has a maximum of 5 inverters. So for systems consisting of Tauros, it's basically going to have the start topology using the router or switch, and then basically have one of the Tauro as the designated master of the system. So in a case whereby multiple inverters are connected in a particular system, say ranging up to 20 or more, it is pertinent to note here that depending on the solution that is being implemented, take for example PV genset solution, where communication latency is needed to be brought to the barest, meaning that the speed of communication has to be top-notch, it is important to note here that we can keep the number of inverters in this system as low as possible, possibly 4 or 6. But then if we must go higher than that, up to 20, then it might be imperative to implement a third-party plant controller. So another new feature that comes with commercial inverters is asymmetric production. So as we all know, previously, the outputs of our inverters are symmetric in nature, but then we now have the possibility with the software upgrade to achieve asymmetric generation, meaning that you can have power being drawn with respect to the particular load demand per phase. So this is basically it, but just to note here that yes, it's also coming with the latest update, and that the 33% of the you can have a maximum of 33% asymmetry, and this is basically for systems with single Gen 24 and back system. Yeah. So finally, just to give us some installation hints for PV array racking system, it is important to ensure that the modules typically roof mounted for residential and commercial and industrial. Please ensure that we have special build structures for this, and ensure that all the accessories are obtained and implemented. Of course, beware of mounting recommendations and modules from manufacturers. Also ensure that structures which must carry this installation are up to par, so as to withstand forces from nature, basically snow, rain, or wind, for example. And yeah, ensure that appropriate interconnectors or interconnecting tools are used to implement all these installations. So basically, these are basic rules and stipulations that are to be observed. So for DC cabling, ensure that the cables are correctly sized. This is absolutely very important, because if they're not correctly sized, you might end up oversizing or undersizing a particular system or cable. And then, of course, try to avoid common mistakes like incorrect string, unconnected strings, reverse stringing, and then, of course, string swapping. Regarding connectors, ensure that you print all your connections properly, and then ensure that the cabling work is basically neatly done. For overvoltage protection, as David has mentioned earlier, we are proud to say that we have implemented this in the battle, just like we have for the tower. So you can see from this back view of the battle, you can see that both DC and AC SPD has been implemented. So you can either come in either type 1+2 or type 2, depending on the specification and nature of the region of installation in play. So for AC cabling, please ensure that all cables are correctly sized, as earlier mentioned, both of course for the DC. Ensure that there are no grounding anomalies. Ensure that all cases of high resistance are attended to. And then, most importantly, ensure that your breakers are appropriately sized and, of course, optimal working condition. Otherwise, we might end up having problems such as these. Great. So that brings us to the end of the presentation for today. Left for the pack, just to give us some extra information, that recordings are available on our homepage, where you can get operating and installation instructions, of course, by using this link. Better still, on our YouTube channel, you can actually find how-to and installation videos, especially those of our webinar recordings. And us there, you can find our Sub-Saharan Africa playlist, which comprises of a compendium of all the webinars that we have produced so far, including this one, which will be uploaded subsequently. And then you can have access to these webinars through this particular link. For technical questions, training, sales, and after-sales service, please do well to contact us via this contact information on your screen. But if you want to get in touch with us directly, that is the technical sales advisors, please do so according to your respective technical sales advisor for your region. So myself, Cyprian Okolo for the Western African region, Byron Kotze for the Southern African region, and David Mwangi for the Eastern Africa region. So with this, we have come to the end of today's presentation. We're hoping that you enjoyed the content, and until we come your way next time, thanks for attending and goodbye.